been years ago now, and I've learned a thing or two. And yeah, today I'll be going over just the most basic information that you guys will need to get started running R, and then hopefully the script that I share will be useful to you as you learn more about how to do your own statistics for whatever projects you might have going on. Okay. That looks like up there. Okay. Guess I can just shrink that. If there's any comments, if one of you guys could let me know. Okay. Alrighty, so this is so just to let you know, can you see the chat? Okay, I won't do that. This is what our studio looks like. So tonight, you don't need to have our studio up and have the script running with me, but you can if you want. But I'll show you how the script works, and I'll introduce you a little bit to how our studio works right now. So this is our studio, and there are 4 windows that you can see here. So the primary window here in the top left is where your script is. So our script is where you write the code, and that's where you it's like basically a Word file, but for R. And then in the bottom left here is the what is this called? The console, and this is where the results of any function that you run will be shown. So if I run this one function right here, you'll see that it pops up down here, and that means that that function ran successfully. So that's where errors and stuff will show up. Over here on the top right is your global environment. So this is where objects will be stored. This is I'm on a project that's pretty large, so I have a couple hundred objects in my global environment right now. But yeah, so data files or like data sets that you make, variables you make will show up here, and we can see that in just a second. And then down in the top or the bottom right is kind of a helper window. So there are a couple of things you can do. It will show you plots. So if you run a plot, it will show up there. This is also where you can download packages, and a package is like a supplemental group of functions that you can use in addition to the functions that base R has. And then you can also, every function usually has a help section to it. So I was looking at the help section for a function called Adonis, which we'll maybe get to today. And then, yeah, so those are the 3 major things that you'll find down here in the bottom right corner. So just a couple of things to start off that I like to remind everyone about or let people know about. The first one is where is it? Yeah, to go to, I'm on a Windows right now, so it might look a little different if you're on a Mac, but to go to global options. And then there's a couple of things that I like to do straight off. So if we go to code and then make sure that soft wrap R source files is checked. And what that does is if you see here, this line is just a continuation. So it basically just wraps it down to the next line. You'll see there's a little gap. So instead of just going off to the right indefinitely, it'll bring it down for you. It's really very useful. And then the other thing is appearance. So I have, what is the one I use called? I have pastel on dark, the theme, but you can change it to all sorts of different themes. So you're welcome to practice with that or check those out. Okay, so let's get into this script here. So this is what a script looks like, and you'll notice that there are two distinct groups of lines here. So there are comments, which on mine are blue. And to make a comment, you put the pound sign or a hashtag, and then you can write anything, and that won't be mistaken as a function. And then functions are everything else. So any line that's not commented out will be run, or will try to run it as a function. So the first thing that I like to do when starting a new R script is to set my working directory. And the working directory is basically the folder where you're going to save all of your content. So for tonight, I just have mine saved on my desktop. But normally you would want to save this in like your seeds / like R nights folder, or wherever you want to store your data. And to run a line of code, you don't just you have to press Control or Command Enter. So I'll hit Control Enter here. You'll see again it pops up, and that means that if I bring in a data set, or if I want to add a new data set, it's going to pull it by default from this folder. So this is really useful when you're importing data sets, or exporting graphs and stuff like that, so you know where everything will be saved. Okay, so let's just get into some of the very basics about how objects are made in R. So an object is just anything that you name. So you can name pretty much, you can name lots of things, and they'll become objects. So the most simple form of object is just like one number. So if to name an object, you just use an arrow, just like that. And if I hit Control Enter here, and then I run the name of that object, you'll see it pops up down here as 3. And then you can use that as a replacement for like the number 3. So if we did test variable plus 6, that's 9. Test variable times 4, that's 12. So this is how the most simple objects work. And that's not very useful when you are just using single numbers like that, but it becomes very useful when you have two-dimensional data sets, or in our next instance here, just a one-dimensional data set, which is a vector. So we can create this vector, and then if we do test vector plus 3, it will add 3 to every number. And that's how you can manipulate a column. So this is basically a replicate of a column inside of a data set. And we can rename that using the named object. So test vector plus 3 is just every one of those numbers plus 3. And to examine specific cells within an object, you can use a couple different methods. So the most basic method is to call it by number. So if you use brackets, this line here will find the third object in this vector. And then we can run a logical test, so pulling out anything inside a test vector that's less than 8. So 4, 6, 7. And this is how that works. So it runs the logical test inside of the bracket, true and false, and then it will spit out whichever numbers are true. And we can do the same thing here just as an example. So whichever sorry, yeah, so within test vector b, we can find where test vector, the original one equals 3, which would be 6 because 3 plus 3 is 6. And then to plot this in the most simple way, there's just the basic plot function. So if we won't run this line of code, it'll show up over here. And we can look at this, which is just a straight correlation. And then, like I said, we can use a question mark, and that will bring us to the help section. And we want the generic XY plotting. And then this tells you all about the function. So what variables it requires, and all sorts of other technicalities that you can use to personalize plots and so on. And moving up from vectors, we can make data sets or 2D objects really easily just using the function called data.frame. So if we combine test vector and test vector B, using that, we now have a data frame. And this is, you can think of it as like an Excel sheet, and you can export it as an Excel sheet if you desire. Okay, so that's just some of the very basics of how objects work in R. And now let's use an actual data set. So this is data that the UCR seeds group collected in the spring of 2022 at the, what is the Santa Cruz Islands. So that's what SCI stands for. So to upload this data set into our script right now, we just use this function called read.csv. And because this is on my desktop, it will load in, and you can see that it popped up here. And if we click on that, we can take a look at this data set. So here is basically the, let me show up like that, sorry. The raw data from this project where the seeds group went out and did species or they collected data on species composition of plants and transects that either did or did not have sheep grazing at them. And really quickly, another way to import a data set is you can do it manually up here. So that's another option as well. So if you want to take a quick look at what a data set looks like, you can use the function head, which will show you the first 6 rows of the data frame for each column. So that's what we have down here. That's the first 6 rows of everything. And then to go back to using brackets, we can use brackets in the same way that we did with vectors, but it's just a little bit updated with a 2D data set. So how it works is bracket and then X and then Y. So if we want to display the third column, we leave the row, which is the horizontal aspect of a 2D data frame, empty. And then we do (3). So this will show us the third column. You see it just has names, or these are codes for different plant types. And let's see, let's take a look at the second column here. So the second column has dates in it. So when R imported this data set, it converted what was a date format in Excel into a series of 6 numbers here. So this isn't useful to us, and R doesn't recognize it as a date. So we want to fix that. And we can do that really easily using this function called lubridate. But first we need to install the package. So when you are using anything that's not in base R, you need to install the package. So, and you only need to do this once. So you can either use the function install.packages, or you can come over here we can search for Lubridate, and there it is. So I already have it downloaded or installed, so I won't run that. So after you install it once, you don't need to do it again, so I comment that out. But anytime you close an R script and then open it again, you do need to add it to your library, and that's so R doesn't become really bloated and have all these packages ready to go at any time. So you need to add it to your library whenever you restart. So let's add this package called Lubridate. And then the function inside of Lubridate is this function called YMD, which just says year, month, day. And we can take a look at that. So basically you just add in the column, and then YMD is, we want it to be in year, month, day format. So that's how we will run it. So inside of our bracket here is the raw data, and we'll run this function and overwrite that column. So I'll run that function, and then if we look at this again, you'll see that now it looks like a date, and it will be treated like a date in R, which is really important if you're working with time series. Okay, so in addition to pulling columns, you can also do the same thing with rows. So if we look at the fourth row inside of our data set, this is every column for the fourth row. And then if we want to look at the fourth row on the second column, so look at that date, we can do that as well. So there's the date for that specific column and row. In addition to using brackets, you can also call columns using the money sign, which is it's kind of easier because you can, if you have an object and you put in 3 characters of the name, it'll pull up the list that fits that. So if we find sci.dat and then use the money sign, it will show us the names of all of the columns here. So instead of searching for the second column using brackets, we can use the money sign and we'll pull up the exact same thing. And you can do that with any column like that. And if you want, you can technically combine the two. So put the name of the column into a bracket like this, and it will pull it up, but that's not the most time sensitive method, so I don't suggest that. Okay. If we want to look at all of the column names, which can be useful if you're trying to organize stuff, and I'll show you an example down below. You can use the function call names. So this is just a list of all the names in the column. And we can rename a column really easily just by, we use the names function. So this shows you all of the names. And then we pull specifically the second one. We can rename it to date of date if we so choose, but that doesn't make any sense, so we'll rename it back. And we can write over columns, like I said. So if we want to add a new column called DDD, which is just a dummy column name that I use for when I'm quickly making stuff, we can write over that. And then if we look at sci.dat again, you'll see that it's added right there. This is the DDD column that I added to the end of the data set. Okay, so that's a quick intro into how data frames work. And again, a data frame is like an Excel sheet, so you can technically import Excel files using this button or I think it's read.excel, but the preferred format for data sets is a CSV, which is a comma separated value file, and those are preferred because they are much more compact in terms of memory. So, and you can easily save an Excel file as a CSV if you do save as, so just something to keep in mind. Okay, let's move on now to how to visualize data. So like I said, there is the basic function called plot that you can use, and there are some people who are like base R plot people, but I conceptually disagree with that because there are better ways and I think more intuitive ways to make plots. And the main package to do so is called ggplot2. So we'll add this to our library. And again, if you're doing this for the first time, make sure to put install.packages that, and I won't run that, so I'll comment it out. So add ggplot to our library, and then we can start making plots. So just to introduce you to how it is organized, the first part of the function is the data set that you're using. So we're using sci.dat, and then to specify the x and y variables on your plot, you put them inside of this AES function, which is called or stands for, aesthetics mapping. So this is just ggplot's method of specifying what you're putting on the axes. So we're going to take a look at plot cover type. We have bare ground, forbs, grasses, thatch, and trees, and we're going to make a histogram. So in order to make a plot, you need to first put in where you're getting your data, and then what's on the X and Y axis. And then you use a plus sign, and then you specify the kind of plot that you want. So this is what makes ggplot really useful, is instead of putting like 30 lines of code inside of the plot function, you can just use a plus sign and add pieces and manipulate specific parts of a plot. So let's run this and we can take a look at what that looks like. Okay, so this is what a base ggplot figure will look like. So on the x-axis, we have plant underscore cover underscore type, and then it takes all of the data from that column and inputs it here on the x-axis. And on the y-axis is just how many times each type of a ground cover was documented. So you can see bare ground was rather common, and trees were pretty common as well. So this isn't, so that's just one way to like count your data, which is useful using a histogram. But now let's start asking some potentially more interesting questions. So our first question that we'll visualize is, how does total cover height differ between ground cover types? So you would expect trees to be taller than, or the tallest group, right? And bare ground shouldn't have any height. So we have on our x-axis plant cover type, on our y-axis total cover height in centimeters, which is just another one of the columns. And then we're going to use a box plot. And just to show you how many types of how many types of graphs you can make, they're all within the geom function. So these are all different types of plots that you can make if your data requires that. So lots of variability and potential there. So let's run this box plot. Ooh. Sorry, the function is not doing its job. Okay, there it goes. Sorry, my computer's acting a little slow here. Okay, so here we have the types of ground cover on the x-axis and height in centimeters on the y-axis. So this is the most basic way to visualize that, and you'll notice, well, one glaring problem is that we have missing data here as a group, and we don't want that, right? That's not very professional to have missing data in your figures. So to fix that, there's a lot of easy ways to do it, but the easiest way is to use a package called Dippler, which is in the greater realm of this group of packages called Tidyverse, and I'll show you guys that in a couple of minutes here. So just really briefly, we'll add Dippler to the library, and then what we're doing is we're going to filter out this missing data. And so what this symbol is here, the percent greater than percent sign, that basically stands for the words "and then." So we have our data set, and then we're going to filter out the missing data, and then we're going to run our box plot again. So if we run this line of code, you can see that we've gotten rid of that missing data. So this looks a little bit better. And like I said, the great thing about ggplot is you can manipulate every single aspect of this figure. So if you take a good look at this, we're going to make it look more professional now. So we're going to do the same filtering process, and this time we're going to update the axis labels to words instead of just the column title. So now that looks a little bit better. And then we can change the theme. So right now it's on a gray background with white borders, and that's the base theme. And I prefer the theme called theme_BW or black white. So it changes it to look like this. And just to show you, there's lots of different kinds of themes here. So yeah, you're welcome to pick your favorite and go from there, but I prefer the basic black and white one. And you'll notice well, to me, the box plot from a distance might be hard to read, so we can update the thickness of the lines, and you can do that using this CEX variable inside of the box plot. And an easy way to figure out how to manipulate stuff like that is just to go into the question_box plot. And here it shows you all of the different ways that you can manipulate the specific box plots. Okay, so we have this one. And a real benefit of ggplot is you can layer plots on top of one another. So this shows the distribution of the data, but we can add the raw data on top of it, which is potentially useful. So if we add in this geom_point on top of the box plot, that's what it'll look like this. So that has all of the raw data on top of the box plots. And that doesn't look very good, but there's ways to improve it. So instead of using geom_point, we use geom_jitter. That moves the points horizontally. So now you can see where the data is a little bit better. And by adapting the geom_jitter, so we're going to add this alpha equals 0.5. That makes the points slightly translucent. And then width decides how wide they should be jittering. We can make a figure that looks like this. So this, to me, has a good visualization of how the data set is distributed. Okay, and let's move on to look at figures with continuous data on both the X and Y axis. So if we do the same filtering process, we can look at how the transects that were used to find or to quantify the species composition were 30 meters long. So let's just pretend that that's biologically relevant, and we'll make a figure that has meter 1 through 30 on the x-axis and then total cover height on the y-axis. So that's what the raw data looks like here. And like I said in the beginning, this project was, one of the goals of the project was to determine if there are differences in the species composition of plants along transects where there were sheep that could graze there, and then differ between plots where sheep were excluded. So now we will add in the difference between the sheep and no sheep plots. And you can do that. What we're doing here is adding in this section inside of the base ggplot function. So we're filling the points with the color, or with treatment, which is, yeah, so let's see. So all we're doing here is this is the exact same function as this one, and the only addition is that we're adding color and fill right here. And so treatment, if we look at the data set, it just says sheep or no sheep. So, and you can see it shows up over here, sheep or no sheep. So we just add the color and fill to it, and then that will color these points. And then if we, oh, I skipped ahead. So if we, let's see. If we want to know what the trends look like, that's usually what we're trying to do, is determine if, for this instance, if there's a difference in the plant height between the two groups along the 30-meter transects. So we can add regression lines to them. And to add a line like that, you use the function geom_smooth. So if we just put that in there without adding anything else, it will create a lowest curve, which is just adding a best fit curve based on the data. So like going through the average in a smooth way. But this isn't how we professionally are going to add regression lines, right? We typically want to add linear regressions. So to do that, we just have to add this method equals LM, linear model, to the geom smooth, and then we'll get nice straight lines here. And we can remove these error, the 95% or the confidence intervals here, if we put in SE equals false, so standard error equals false, and then I'll add in CEX, which just has to do with the thickness of the lines. So you'll see I thickened the lines and I got rid of the confidence intervals. And now we'll make it look a little more professional. So we'll add axis labels and then change the theme. So that looks a little bit better. And then you can update the color or the treatment labels using the add-on scale _color _discrete. So we change it from no sheep to sheep to not sheepish and sheepish. So this is a fairly, this is potentially a figure that you could use. And you'll notice these two colors that were selected are the default colors. So salmon and like light or like ocean blue are the two default colors that ggplot uses. And the third one I think is a green if you have 3 groups. But there's ways that you can personalize that. So one of the easier ways is to use this package called R Color Brewer. And it has a variety of palettes with a bunch of different colors that you can use to personalize your figures. So I'll just show you a couple here. Let's see. So what I did is, where is it? Yeah, so we're using this function scale underscore color underscore brewer, and that allows you to add a specific palette. So we added this palette called set1, and we can do that again. So these are the base colors here, and we can change that to a palette that's a little more visually appealing. And there are hundreds of these, so if you follow this link here, you can check out all the different palettes. Okay, so that's a little bit about data visualization. And now I'll get into probably the most important part of using R, or at least something that you'll end up spending the most time doing, which is organizing your data. So to do that, we are using tidyverse. So tidyverse is a group of packages, mainly Dippler and Tidier. And I think, let's see. Yeah, you can import all of them using the using library tidyverse. Hopefully that doesn't mess us up here. Okay, we only need these Dippler, Tidier, Reader, and Broom. So yeah, R does update, and which can be a scary thing if you're like in the middle of a project and you have to update R, and then packages don't necessarily update simultaneously. So this error here is telling me that there's a difference in my version of R versus what the package tidyverse was built in. Okay, but that's not detrimental to using this script here. So now let's think about this data set a little bit more. So this is what the data looks like. And in each row here is basically one, sorry, my computer is not super happy right now. So each row indicates one or two plants, or it's a one quadrat, right? So each row is a 1 by 1 meter quadrat. And in here, we have the identities of the plants that were inside of the 1 by 1 meter quadrat. So we have this, I'm going to guess a lupin, and then this other plant, mycol. And this is how data is typically collected out in the field. And what we're going to do is take this data set in its current form, which is not very usable for statistics, and we're going to convert it into a data set that you actually can do statistical analyses on. So a huge part of using R is that you can easily manipulate your data into any format you need it to. So just keep in mind that we're starting out with these up to 4 columns here that have the up to 4 different species per quadrat. So what we want to do is first put those 4 columns and make them into one column. That way we don't have to work with multiple columns, because you can't analyze 4 columns at the same time like that. So using tidyverse, we're going to take the data set and then we're going to pivot it longer. So we're taking the 4 columns here and we're going to basically stack them. And then we're going to omit the missing spaces. So if we run that, we have this new object called sci.long. You'll see it's quite a bit longer, 3,000 rows versus 960 rows. And what we've done is, it's at the end here. So we have this column now that's basically the culmination of those 4 columns. in the base data set. And what it did is it copied over. So our first two rows here are from the same quadrat. So all of the information here is going to be the same for every other column. But there's a difference in the name of the value for that plant. So now we want to add up the different types of species in each quadrat. So what we're going to do is take our new data set and then group it. So we'll group it by treatment, which is sheep and no sheep, and then we'll group it by transect. So is it 30 transects? Yeah, 30 transects. So basically within each treatment and within each of the 30 transects, how many of each species were there? So, and then we'll count it. So I'll show you, we updated sci long, so it went, or SCI long, so it went from 3,000 down to 200 rows. And if we take a look at this now, we'll see it's a lot different. So we have how we separated them, treatment and transect, and then we counted the values. And then in here is the number of times that plant species inside that transect, inside that treatment were present. So this is starting to be useful data, but you'll see that there's a bunch of values here that are missing, and that's because in our original data set, you'll see all these blank spaces. So we want to get rid of those blank spaces. They don't mean anything to us. So we're just going to use the handy filter function and get rid of them. So if you see it went from 209 to 169, and now we have just data that is useful to us. So this is how many times each plant species was in each transect. And we can take a look at this. So this is a histogram of each plant species. So plant species on the x-axis, and then the number of times the plant species was counted on the y-axis. So you can see this Eriogonum species here. Eriarb was the most prominent plant species. So at this point, this is a pretty good and usable data set, and we just need to do one more thing to transform it into a data set that we can do community level statistics with. So to make, and so we're going to make it into a data matrix. So we take our long data set and then we're going to pivot wider. So we started by pivoting long, now we're going to pivot wide. And what this is doing is it's taking each value and making it its own column, and then taking in and filling in the rows. So I'll just show you what that looks like. What was that called? Wide. There it is. There it is. Okay. So like I said, each plant species now has its own column, and then where it was present, it'll fill in that number for how many times it was there. And we don't want the NAs in there, so we'll convert the NAs into zeros. And now we have this very nice, pretty data set. So we went from these 4 columns that are not useful to us, and we've converted it into this data matrix that we can actually use to perform statistical analyses with. So before we get to community level statistics, I added a little bit in here just about some of the most basic form of statistical tests. So the most simple form is a t-test. So let's see, if we look at this plot here, so going back to the basic data set again, sci.dat, and we have treatment, so sheep, no sheep, and then total cover height. And we have this this trend here. So we want to know whether or not these two groups are significantly different from one another. We can do that using a t-test. So to perform a t-test, you need to basically the two parts of the data that you need to add in is one row with one column and one row with another column, which means that we have to separate them out manually like this. So we have the sheep data set, and then the no sheep data set. And if we run a t-test, we'll get this result where our p-value is less than 0.05, so it's significant. However, that is not the most useful way to run a statistical test like that, because a t-test is basically just a very simple form of a linear model and or linear regression. And linear regressions are the bread and butter of how most biologists and ecologists perform statistical analyses. So we can run the same test using a linear model. So the basic linear model function is this ln. So this is how the script is written. So we have our response variable here, which is cover height, and then treatment, which is sheep or no sheep, and then our data. So if we run this function, we get a summary of it. You can see that we can prove that we have a significant relationship here where the p-value is much lower than the threshold of 0.05. And this also gives us the r squared value. So 0.06 is not so bad in ecology. And ANOVA more explicitly breaks down the relationship between factors. So say if we predicted this based off of the transect again, like we made figures for, that was just showing, or those are two numeric values. And if you want to explicitly test for categorical values like treatment, you can use an ANOVA, which just stands for analysis of variance. And you'll see that the results are exactly the same. And I thought I would show you guys really quickly how most professional ecologists perform linear models. So we don't use basic linear models. We use what are called mixed effect models. So what this does is it combines the variables that you want. So we want to test how treatment varies between, or how cover height varies between these two treatments. But say we have a confounding value, or a confounding number, or sorry, we have a confound. So for example, say in the sheep transects, there were more trees, and trees are taller, so therefore it will look like the plants are taller in the sheep transects, even though it's just an artifact of the fact that there's more trees. So if we want to test how each specific type of plant cover differs between the two groups, we can add what's called a random effect. So this is what a random effect looks like. And what this is basically doing is breaking up the data set so that each type of plant cover has an independent y-intercept. And I won't get too much into that, but what it basically does is it removes the confound of the type of plant cover. So if you run this model and we look at a summary of this, it looks different. First of all, the creator of this package, LME4, does not believe in p-values. So it does not spit out one number, but it does give you all the information you need to determine the significance. And that's using the effect size, which is this estimate, and then the error. So if the estimate is larger than the error, and the error doesn't cause the estimate to, or the error doesn't cross 0, then it's significant. So since our estimate is 4.2 and our error is 1.8, we can determine that this is significant, even when the plant cover type is covered, which means that the plants in the sheep transects are actually taller. And we can run an ANOVA now to take a look at this. And again, because it's an ANOVA of an LME4 function, it won't give you the p-value, but yeah, this one actually is not very easily interpretable, but it'll tell us the same thing. So this is just a very brief window into what mixed effects models looks like. And we have 6 minutes here, so I'll really quickly show you what you can do with the data matrix, this SCI.wide data set. So if we bring in this package called vegan, and we relativize the data, we take our predictors, which are the first 2 columns, and then we can, so basically what you want to do, so the problem with community level data like this is that we have all of these columns and all of this information, and there's no good way to resolve that down into like a predictor and a response variable. So there are statistics that people have developed to force complex data like this, multivariate data, onto 2 axes. So I'll just show you a couple of them here. The most simple one, or at least the best way to visualize it, is called an NMDS. Let's see. Oh, sorry, I didn't put the question mark first. So a non-metric multidimensional scaling function. So if we run this, we reach the solution. That's pretty good. If the stress is less than 0.2, that means you're doing well. And then this here is what all of that data looks like in 2 dimensions. So we can look at it like this. So the plus signs are the species and the circles are the sites. So you can see there's like a group of sites over here. There's kind of a group of sites here, and we have these 3 sites up here. And there's lots of ways to look at this. So you can either focus on the sites. These are sites. These are the species. You can, yeah, so you can examine it like that. And there's the function order plot is really useful for that. And one really nice thing is we can add in ways to visualize the different groups. So we can see that the no sheep group is kind of nested within the sheep group. So there are species that exist in the sheep group that don't exist in the no sheep group, but most of the plant species that are in the ungrazed transects are also in the grazed transects. So I'm not super familiar with this, but I think that means that there's probably non-native species that the sheep have kind of allowed to proliferate, I had to guess. Okay, and to analyze this and produce a p-value, you can use a statistical method called a PCA, and this is just another way to examine it, but you can't actually add in predictors or anything like that. Let's see. So you can make these, you can take your PCA and put it into ggplot. That way you have all of the options of a ggplot. And one thing that people do a lot is pull the axes. So if we take the information from this axis here, say like it was very clear, well, for example, like Airy Arb here is having a big impact. The longer the line, the more influential it is. So say we wanted to know just about the first axis here, we can do that. We can pull that information out, and now we have this data, which is, I won't get into it, but that's useful in some scenarios. if we want to run a statistical analysis and determine how treatment impacts community composition, we can use today we'll use a correspondence analysis or a constrained correspondence analysis. So if we run this function, CCA, you see it's built just like a linear model. We can examine it statistically. And these are this again doesn't give you a clean p-value, but it does, you can get an r-squared value. So r-squared of 0.66, that's not so bad. An adjusted r-squared value of 0.34 is it's not so bad either. You can run an ANOVA on that, and then we do get a p-value. So we can see that there's a significant difference between the sheep transects and the non-sheep transects. And then if we want to think specifically about diversity, we can use what's called a permanova, and that's a permutational multivariate analysis of variance. So it's like an ANOVA test, but specifically for this kind of data. If we run that, we can see again that treatment does in fact have a significant impact on the composition and diversity of these plants here. So yeah, this stuff here, if you're interested, I would look through it really closely and maybe search for these functions, because that's just to conclude, one of the great things about R is that anything that you have done, people have already done it many, many, many times. So if you just get good at Googling the right words, like if you Google an error, I guarantee you that someone has already figured out how to do that. And so that's what makes R so great, is there's this huge community of very committed individuals who work really hard to make R, which is free, as accessible and usable as possible. So from here, if you're interested, you can I recommend Googling like a intro to R for ecologists or something like that, because there's lots more packages or lots more scripts that professionals have made that will teach you more. So yeah, that's kind of my ending message. And are there any questions really quickly? If not, we can wrap up. What is the difference between R and Python? I think so Python is more like computer programming, so you can do like non-statistic stuff with it. I think, or that's how I've interpreted what Python can do. And R is more specifically for statistics and data manipulation. So some people do use Python for statistics, but from what I understand, you can do it. It's just a lot harder, and it's a lot more script writing. That's like the major difference. Okay. Alrighty. Well, thanks everybody for showing up on Zoom, and thanks guys for being here in person. If you do have questions, you're welcome to email me. I'll put it in the chat really quickly. And yeah, have fun learning more about statistics and R. Okay.